Hi everybody, and welcome back to another video in my series on computer systems. In this video, we'll be taking a look at the last part of Module 2, which covers machine code. We'll be talking about how data is dealt with when we get down into the level of dealing with machine code. If you're following along in the textbook, this is coming from Chapter 3 of Computer Systems, A Programmer's Perspective. Let's start out by talking about allocating arrays, right? This is something we do all the time. And the basic idea, specifically in C, is that we declare an array and we give it the data type, right? And we'll refer to that as T in the general case, and the length of the array. How many of this kind of data are we going to have in this array? What's the size of it? And that's going to end up being a contiguously allocated region of L times the size of T bytes in memory. So just however many of whatever type of thing we have, multiply that by the size in bytes of that type. That's how much of memory we're going to allocate. And for an array, that memory is always going to be contiguously allocated. So we see some examples here. For character type arrays, you remember a char is only 1 byte, so we're going to have a total of 12 bytes allocated for a char array with a size of 12. Integers, on the other hand, have a length of 4 bytes. So if we allocate an array for 5 integers, we're going to have a total of 20 bytes of space allocated again contiguously, right? This all has to get allocated together. We can actually use pointers for this stuff too. So if we declare an array of type int and length 4, right? If we index into that array, so there's this val at index 4, we're just going to get the value that's stored at that spot in the array. We can also get pointers to the address location, right? So we can actually use that asterisk that we see when we deal with pointers, and we can actually go ahead and find out that, val is stored at X location, at the memory address X. We can find out that val plus 1 is stored at X plus 4, etc. We can also use the ampersand to return the address of a certain index of the array. As an example, let's just take a look at a little bit of C code that just creates a type, right? It defines a type, and it makes this zipdig array that's just an integer array. Okay, and we'll go ahead and create 3 of those, right? We'll call them CMU, MIT, and UCB, and we'll just give them 5 integers apiece to just set that data in those arrays. So as we can see, the CMU array ends up starting at address 16, and we've got 20 bytes of memory allocated, and what we've got stored in those locations are those integers that we specified. Because we've taken up those 20 bytes, MIT starts at 36, and we have 20 bytes for that. UCB starts at 56. We have 20 more bytes for that. Now, for the example, we've just acted as though they were allocated in successive blocks, but that's not guaranteed to happen in general. Each individual array has to be contiguous, but just because we've declared these one after the other does not mean that all 3 of them have to be contiguous. They don't have to all be together. They could be at very different memory locations as long as each individual array is allocated in a single contiguous block. So how do we actually access a particular element of an array? Well, happily, that's actually pretty simple. Another little bit of C code here. We just have a little function that gets us a digit out of one of the arrays. We pass it the array as the first parameter and the digit that we want, right, the index we want to go to as the second parameter, and just return that array at that index. Now, the first parameter always goes into RDI. The second parameter goes into RSI, right? We've seen that before. So RDI would contain the starting address of the array, and RSI would contain the index that we want to go to. So we can just go ahead and move whatever's at that memory location into EAX. Remember, that's going to zero out the rest of RAX. So it's a simple one command assembly code, right? It's just going to use that memory addressing that we talked about a couple videos ago. And the desired digit will be at RDI plus 4 times RSI, right? So we can see that this works. If we passed in the CMU array, then RDI is going to be storing memory address 6, is going to be storing a 16 to indicate that we're going to memory address 16. And if we pass in 0, we just want the first element, then 4 times 0 is 0, so we're just going to go to memory address 16. We're going to get that first element of the array. If we want what's at index 2, then we would pass in a 2. We'd go to 16 plus 8. That gets us to 24. And hey, there is the element that's at array index 2. So we can actually do the math on this one very easily and see that this works. And it's just this simple to access an element of an array. Now, looping through an array is also pretty simple. I mean, it looks a little scary, but machine code often does. But we'll go through, we'll take a look at this line by line, and you'll see that this is a pretty simple thing. So our C code is just going to have a little function here that just increments every element of whatever array we pass it. All right, so we're just going to pass it one of those arrays that we've created. And then for I equals 0, and while I is less than the length of the array, we'll increment I, right? That's just setting up our for loop. And then the only thing we do within the body of the loop is increment whichever index of the array we happen to be looking at the time. So whichever index I reflects, we'll increment that by 1, and we'll just do that all the way through the length of the array. So let's dive into the machine code. First thing we'll do is set things up. Now, remember, RDI gets our first parameter, so RDI is going to have the address of Z. So we'll move a 0 into EAX. That's just going to zero out our return register, right? And we're actually going to be using that as our loop counter. Our return register will be used as the counter for our loop. So we'll zero that out because we're always going to start at I equals 0. And then we'll use this go to middle approach to looping that we talked about a couple videos ago. So we'll jump, an unconditional jump. We're always going to do this. We set things up, set up our index, and then we jump to L3. Now down here in L3, we're going to do a compare. We're just going to compare RAX to 4. Remember, that does RAX minus 4. If it's less than or equal to, so this jump if below or equal, to L4, that means we jump back up to the body of the loop. Now, we've got 2 adds here. Why is that? Well, keep in mind that when we deconstruct a for loop, we have to take care of the loop counter as a separate thing. So this first add that's in red is just going to add 1, and oh, hey, look, there's that memory thing that we talked about before, right? This memory address. We're going to take 4 times RAX. Remember, we're dealing with an integer array, so each one is 4. So we're just going to have RDI as the start of our array. We add the index times 4 to that to get to the appropriate element of the array, just like we talked about in the last slide. So we do that, and we go ahead and that add just increments that element of the array. Then the second add, we're going to add 1 to RAX. That's incrementing our loop counter. We fall through L3, we compare again. If it's below or equal, we go back up to L4, and we just loop through until the index is 5, right? Until the index is not below or equal. And we don't want to run the loop when the index is 5, right? Well, that's in the for loop. That's us checking our stop condition and saying, aha, I is equal to the length of Z now, so I do not want to execute my loop one more time. I want to fall back out of it. So when that happens, we skip the jump if below or equal, and we just go right to our return. So again, it looks a little complicated, but when we follow the logic through, we find out that looping through an array is another thing that's a pretty simple thing to do. So what about multi-dimensional or nested arrays? Surely that's gotta get way more complicated, right? Well, it really doesn't. When we declare a multi-dimensional array, and with some languages we can just declare them as we see here, where we specify a type and then instead of giving it just one length, we give it two. We give it R and we give it C, our number of rows and number of columns. And of course, our rows would be indexed from 0 to R minus 1. Our columns would be indexed from 0 to C minus 1. Okay, and so that's fairly straightforward. We might, in some languages, also have to declare this as an array of arrays. We might have to create an outer array, the elements of which would just be the other arrays. But either way, it ends up accomplishing the same task. So our size is just going to be our number of rows times our number of columns times the amount of bytes that each element requires. So this R times C times K would give us the entire size of this multidimensional array. And the arrangement is actually pretty straightforward too, assuming that we're dealing with row major ordering, where basically all the rows are stored together, as opposed to column major, where the columns would be stored as single entities. What we'll have is still just a one-dimensional, right? We're just going to lay the bytes out from one end to the other, and we're just going to lay all the entries, all the columns in row 0 together, followed by all the columns in row 1, followed by everything in row 2, all the way up to row R minus 1. All right, so we still just get ourselves an allocation of 4 times R times C bytes, because if we're talking about an integer, we've got 4 bytes per element, that's our K, times the number of rows, times the number of columns, and we just lay them out row by row by row. So this ends up conceptually being pretty simple too. So here we see an example of that nested array approach that I talked about. If we just declare zipDig, remember zipDig is that type that we defined earlier. That's just an integer array of size 5. And we call this PGH and give that as size as well. Then we're just saying PGH will be an array of size 4, and each element within it will be an array of size 5, right? Will be a zipDig array. So the zipDig PGH and the length 4 is equivalent to just declaring a two-dimensional array called PGH with 4 rows and 5 columns. So when we do this in memory, though, it looks the same. We just take each of our arrays, we lay them all out in row order, because we're assuming row major ordering in this example. And so we just get a contiguous bunch of bytes in memory that is long enough to hold 4 arrays of 5 ints each, and we just lay them all out in a line like this. So to access a row of a nested array, we just keep in mind that A at index I, it's just another array of C elements, right? Each row is just an array of as many elements as we have columns. So each element of type T requires K bytes. So the starting address is just going to be the index times C times K, right? Times the number of columns times the size of each element within a column. So if I want to get to A at index I, right, the row that's stored at index I of our outer array, I just take the index of that times C times 4, because 4 is the size, and that lands us out at the appropriate row. So let's just do a couple quick examples. If I want row 0 of array A, then of course I start at the starting address of A. Let's assume that that's 0 just to make things easier. So if I have the starting address of A, which is 0, plus the index, which would be 0, times C times K, oh, well, I just land at 0, so that's pretty straightforward. I'm just going to go out to A, and it doesn't matter if A starts at 0. A could start at 16. I would have 16 plus 0. I start at the start of A. That gives me the first row in A. Now, what if I want to go to row 2? Well, then I take my starting address of, well, let's stick with 16. If A, the whole array, starts at address 16, I take 16, I add 2 times C times K, right? So that 2 times C times K just skips me ahead the length of the first two elements of row 0 and row I are going to have a total length of 2 times c times k. So I start with 16, I add 2 times c times k. That lands me at row 2 of array A. I skip rows 0 and 1, and I've gotten myself to the address of row 2 in array A. Now, to get to an individual element in that row, it's just a simple extension. A at index I, we've already talked about. That's what we just did. That gets us to row I. So then when we specify J in the second set of square brackets here, that's giving me the column that I want within that row. So I just do the same calculation, right? The A plus I times C times K gets me to the appropriate row. Then J times K again gets me to the individual element in that row. So I'm just going to start with the address of the array, offset myself to the address of the row in question, then offset myself again using the second index to get to the individual element within that row that I'm looking for. So let's go ahead and tie this all together just to make sure we're clear on exactly what we're talking about. Let's take a look where we've declared a variable called univ, right, for university, but univ, and it denotes an array of 3 elements. And those elements are going to be those CMU, MIT, and UCB zip code arrays that we created earlier in the video. Now, each element in the univ array is a pointer. Now, pointers in 64-bit architectures are 8 bytes, so we can see that we have a pointer living at address 160, another one living at 168, and another one living at 176, because that univ array has to be contiguously allocated, and it's got pointers in it, right? So we've got 3 8-byte pointers all in a row. Now, we've actually declared the arrays CMU, MIT, and UCB, and we've got them at the same addresses that we saw earlier in the video, but notice that when we use them to initialize this new array, we've put them in a different order. Instead of doing CMU, then MIT, then UCB, we flipped it around and did MIT, then CMU, then UCB. So we take a look and we see that those pointers just point out to those same addresses that we had them at in the previous example. So the first one is going to be the pointer to MIT. That points at address location 36. The second one is for CMU. That points at 16. The third is for UCB, and that points at 56. And each of those is just its own array of integers. So to access an element in one of those zipdig arrays that are encompassed in the univ array, we can just return the index for the row, and we're going to call the digit to be the specific digit within the array that's inside. Okay, and so we'll do a shift left to multiply by 2 squared. Remember, we can multiply by powers of 2 by shifting. And that'll give us 4 times the digit. Well, what's that do for us? Remember, all of our zipdig arrays are integer arrays, so that just gives us the element in whichever array we end up looking at, right? Each of those are 5-element integer arrays. So multiplying by the size of an integer, or 4 bytes, times the index we want to go to, gets us to the appropriate memory offset within that individual internal array. Then we're going to go ahead and add this memory reference and whatever's in RSI. Now, RSI has the digit, okay, and we've shifted it. So actually, RSI now has 4 times the digit. So we're going to get a pointer back to, we start with the displacement for the univ array, right? So we start at that starting address for that array, which was 160 from the previous slide. We're not going to use a base register. We're just going to use, that's why we have that comma there first. We're just going to use an offset register, an index register, and we'll multiply that by the scale factor. That is 8 because univ, remember, that is holding just 3 pointers, and pointers are 8 bytes on a 64-bit system. So multiply the index times 8. That's going to get us, if we want the first index, RDI would hold 0, so that would just leave us at 160. If we wanted the second address, we would put a 1 in. We would pass in a 1 as our index. That would give us 160 plus 8. That's the 168 for the second element, like we saw on the last slide. Okay, we add that to 4 times the digit, because that's what we now have living in RSI. And that gives us the pointer out to the actual element that we want within those nested arrays. So we just return whatever's living in memory at the address pointed to now by RSI, drop that into our return register, and we've done what we needed to do. We've gone out and gotten the element that was sitting out there, the very specific element that we wanted to, out of the individual array that we wanted. So what we want to take away from this is that nested arrays and multi-level arrays, they look very similar, right? When we use them in C, we access them in pretty much exactly the same way. So when we get up into those higher level languages, there's really not an effective difference between the two. We just treat them the same way. But when we look at how we actually compute the addresses we have to go to, they do look quite different, don't they? In the case of the nested arrays, we would start out with the offset where PGH lives, right? The actual memory address where PGH starts. Add 20. Now, where's the 20 come from? That's our C times K. We're keeping internal arrays that are 5 elements long, and they're integers. So that's 5 times 4 is 20 times the index to get us to the appropriate row. Then we do 4 times the digit to get us to the offset within that row that gets us to the column we want. So that's how we do an individual element access in a nested array. In a multi-level array, on the other hand, we actually do 2 memory accesses, because we have to go to the memory to get us to the row first. Then we add our offset to get us to the appropriate column, and that's a second memory access. So we can see these two things, while they look the same in C, they act very differently when we get down to the machine code, and we have to compute them in different ways. Now that we've talked about arrays, let's talk about another very common thing that we see in C, which is the structure, right? This is where we use the struct keyword. We declare something as a structure. And within that structure, we have a whole bunch of different things. We might have integer arrays or various variables, right? We can put just about whatever we want, even another structure, inside of a struct. Now, a structure, just like an array, is going to be represented as a block of memory that's big enough to hold all of the fields. Now, the thing we want to keep in mind, though, is, as in this example, the fields are always going to be ordered according to the declaration, even if another ordering would yield a better, like a more compact representation. So in this example, we declare an integer array A, which is length 4, so that's why it's 16 bytes. We declare a size underscore t of I, that's another 8 bytes there. We've got another struct, and that's okay. That's going to be a pointer, actually. So that's going to be another 8 bytes, and those are always going to appear in memory in that order. So the compiler actually determines the overall size and positions of the fields, because the machine level program doesn't understand what the structure is, right? The machine level program, that's too high level for the machine level code to kind of care about the fact that this thing is actually wrapped in this structure, right? That's something that's added into the higher level languages so that we can use them effectively and makes it easier for us as programmers, but the machine level stuff doesn't care about that. So we have to keep these rules in mind, and we'll talk in the next few slides about some decisions we might want to make and how exactly that's all going to work as far as how it gets represented in memory. Now, there's nothing surprising about how we generate a pointer to the member of a structure, right? The compiler sort of keeps track of where the structure lives. We're going to have a pointer to the start of that structure. So if I want to get an array element, or get a pointer to an array element that lives in that structure, in that A array, I would pass my structure in, right? So I'll give it a pointer to my struct, and I'll give it the index that I want it to go to within the array. And then we'll just go ahead and we'll dereference that pointer. We'll get the struct itself. And then, of course, that little right arrow is how we access an element within a struct. And then we just give it the index of that array that we want to get to, and we build that with a memory address where we start at R, right? RDI is going to have a pointer to R. RSI has the index. We multiply that by 4 because we're dealing with an integer array in this case, and we'll put that into RAX. That's our pointer, right? We've generated the memory address of a particular element within that array A that lives inside that struct REC, and that's what we're going to output. So this is more review of stuff we've done over the last few videos, right? There's nothing new here, okay? This is all stuff that we should be able to sort of figure out by this point. Now, structures are nice because they lead us into a discussion of alignment. We want to align data in memory in certain ways. Specifically, we want primitive data types that require k bytes. The addresses they live at have to be a multiple of k. So if I've got a char that's just 1 byte, it can kind of live anywhere. If I have an integer that's 4 bytes, I want that to live at a starting address that is a multiple of 4. If I've got a double, which is 8 bytes, I want that starting address of that double to be a multiple of 8. So when we take a look at the difference, and we'll get into the explanation of why this happens as we move forward, and it comes down to this alignment concept. If we have this struct where we have a char C, a 2 element integer array I, and a double V, if it was unaligned, we would just pack that all. Again, it has to be in order, right? These are always going to get stored in the order that they're declared. So we'd have the char, then 2 bytes or 2 integers. So that's 2 4-byte integers in a row, and then our double V. No big deal, right? That's exactly what we expect. But when we look at how it would actually get laid out in memory, we'd have our C, but then, we've got those integers, and those integers have to start at a multiple of 4. So we're going to have 3 bytes of wasted space between the char and the first integer. Then we have to have our double, because that's 8 bytes. That has to start at a multiple of 8. So we're actually going to end up with 4 bytes of wasted space between the 2 integers and the double. And that's no good, right? I mean, memory is a finite thing, right? We don't have infinite amounts of memory, so we want to use it as efficiently as possible. And we're wasting 7 bytes in this example right here. So let's talk about the why of that. We'll get into the principles of alignment in the next slide and a little bit after that. And then we'll talk about how we can avoid this problem as much as possible. So we already mentioned in the last slide that if a primitive data type requires k bytes, then the address that it lives at has to be a multiple of k. Now, on some machines, that's required. On x86, 64, it's advised. But why do we do that? Well, the motivation for this is that memory is accessed by aligned chunks of 4 or 8 bytes, and that depends on the system, but the point being, memory gets accessed by these chunks. So it's inefficient to load or store datum that spans quad word boundaries. Okay, so it's fine if we're doing 8 bytes, it's great. I can grab 2 integers within that, I can grab a double, I can grab a char, wherever it happens to be. It's not going to be efficient to have an integer stored with 2 bytes of it in one quad word and another 2 bytes in another quad word, a different quad word. We're going to have to do more memory accesses to get the whole thing. Virtual memory is even trickier when the datum spans 2 pages, and we'll get into virtual memory later on in future videos. So what the compiler does for us is it inserts gaps into the structure to ensure that each of the fields is aligned correctly. So it helps us as far as the efficiency goes there, but that can be detrimental to the efficiency of our space usage. Right? If we're not careful with how we set our structures up, we can end up wasting space and memory because the compiler is going to put those gaps in to make sure that our fields are aligned properly. So for our various sizes of the different types of things that we can have, we've got the restrictions that their size demand. For a 1 byte char, right, there's no restriction on the address. Yeah, that's never going to span a quad word because it's only taking 1 byte. It's going to be in one or the other. If we've got 2 bytes for a short, the lowest 1 bit of the address has to be 0, right? Because a lowest bit of an address in binary, remember, that means we're divisible by 2. That's an even number. So that's going to be divisible by 2. And binary actually makes it pretty easy for us to move up for these other types as well. If I've got an int or a single precision float, I'm going to have 4 bytes. That just means, again, binary makes it easy for us. The lowest 2 bits of the address have to be 0, 0. For doubles, longs, double precision floats, the lowest 3 bits have to be 0, right? Because that means that it's divisible by 8. For 16-byte, like long doubles, the lowest 4 bits of the address have to be 0. So that makes it a little easy for us to sort of figure out what the addresses need to look like for our various sizes of data types. So at that level, it's pretty simple, right? We just make sure that for whatever kind of data we're using, whatever type, that it lives at an address that is a multiple of its size. Yeah. Now, within structures, it gets a little more complicated, but really not that much. This is actually still fairly simple. Within the structure, every element has to satisfy its own alignment requirement, right? So the char can live anywhere, right? An integer has to live at an address that's in a multiple of 4. A double has to live at an address that's in a multiple of 8. So that's easy enough. But what about where we put the overall structure? Right? We actually do have to align the whole structure itself. Now, each structure is going to have an alignment requirement k that's going to be equal to the largest alignment of any element within that structure. Okay, so the initial address and the length of the structure both have to be multiples of k. So for our example here, the longest element that we have, right, the largest thing we have there is that double. That double is an 8-byte thing. So our structure has to start at a multiple of 8. Okay, so our first address, where that char actually is in this example, has got to be a multiple of 8. That can be 0, 8, 16, 24, right? But it can't be 12. It can't be 22. Okay, it's got to be a multiple of 8. And the whole length of the thing, right? Instead of just allocating the 8 plus 4 plus 4 plus c, that's only 17 bytes for the actual stuff inside the struct. But we're going to allocate 24 for it because we have to have the length be a multiple of 8. It can be 24, it can be 16. Well, it can't be 16 since we've actually got these this mix of elements. We've got 17 bytes of data total within the thing, so it can't be 16 long. It's got to go all the way up to 24 because once we get past 16, because we've got that double, it's got to be a multiple of 8 that is both where it starts and the length of the overall struct. So even if we shuffle things around as we see here, for this specific example, this is not always going to be the case, we actually end up still having the same size for the overall struct. Even if we shuffle things around, do the double first, then the integer array, so the integers for that, then the char, we're still going to have that same 7 bytes of wasted space because of the fact that the overall structure has to have a length that is a multiple of k, and we get that k from the largest alignment requirement within the struct that's coming from that double. Another thing to keep in mind, because it seems maybe intuitively like this may change things, but even when we have arrays of structures, the overall structure length has got to be a multiple of k, and we have to satisfy the alignment requirement for every single element. So even if I've got an array of 10 structures, right, I'm going to have all these structs laid out in a line in memory. Each individual one has to meet the alignment requirements, which means I can't just sort of multiply things out and try to save some space somewhere there. Every individual element of that array A is a struct, and each individual struct has to meet its alignment requirements. So that first struct, index 0, would have to go from the starting address of the overall array and then to 24 bytes past that, right? We have to have 24 bytes for that whole thing. Then the next one is going to have 24 more bytes. The next one would have to have 24 more bytes. So the more of these we string together, the more space we're wasting. We're going to end up wasting that 7 bytes per element of the overall array. Now, the last thing to keep in mind is that even though in our previous example, shuffling around the order in which we put things didn't actually save us space, in a lot of cases it will. And the other thing that we can rest assured of is that it's not going to cost us more space. So this gives us an idea of a good general practice, which is when we're creating a struct, put the large data types first. Okay, so in this example, if we set it up so that we have a char followed by an int followed by a char, right, we're going to have that char. Then the next thing is an int that's got to start at an address that's a multiple of 4, so we have to waste 3 bytes. Then put the int, then we can put the second char, because again, that can go anywhere. But keep in mind that the overall length of the struct has to be divisible by 4 as well. So the C plus 3 bytes is 4. The I is another 4. D plus 3 bytes is 4. We still have to waste 6 bytes. But if we change that around and look at S5, we put our larger data type first. So we put that int first and then our chars. Well, now we can have the int right at the beginning. The C and D can just get packed right after that because those can go anywhere. Now, again, the overall length of the struct has to be a multiple of 4 because our K is 4 from that integer being in there. But the 4 bytes for the integer, then 2 bytes for the chars, we only have to add 2 more bytes of padding to get to a multiple of 4. And we just saved 4 bytes, right? Instead of wasting 6 bytes, we only have to waste 2. So again, this is a good general approach. It's not going to cost you extra space, and it might not save you space, depending on the combination of things you have in your struct, but in many, many cases it will. So we always want to keep that in mind and try to apply that when we're coding. So walking away from this video and from the entirety of Module 2, this is the end of our Module 2 videos. We've gone through arrays, how the elements of arrays are packed into contiguous regions of memory, and that we use arithmetic on the indices to locate individual elements. And for nested arrays, we actually can do the same thing. The math is a little bit more complicated, but not by much. We just go to the index where the row is stored and then go to the index for the column within the row, and we use the same kind of math to get to both of those places. For structures, we want to keep in mind that elements are packed into a single region of memory. They're accessed using offsets determined by the compiler, and it's possible that internal and external padding might be required to ensure alignment, right? We keep those rules in mind. Each individual element has to start at an address that's a multiple of its length. The overall structure that encompasses all of whatever elements you have inside that structure, you take the largest one, and the whole structure has to be a multiple of the length of the largest internal element, and it has to start at a memory address that's a multiple of the length of the largest internal element. And keep in mind, we can do these things in combination. We can nest structures, we can nest arrays arbitrarily, because when all is said and done, in machine code, we're just looking at memory as this one long one-dimensional array that we're just dropping things into in particular orders that allow us to visualize things and use multiple dimensions in those higher level languages.